We were told by the instructor to find the mistake in this flowchart. We spent the entire class, 50 minutes, in a group together, consisted of 5 or 4 people, trying to find out what is wrong with this equation. I found multiple things before I presented to him. I wanted to make sure that everything was right. I said, instructor, the flow rate that will come to the reactor is not equal to the flow rate that will leave the reactor. But the problem is the units are in moles. It turned out that the issue is much simpler than we thought. Look at the mixing point. The streams are not equal. Then he followed up with a question. Why? Why the moles are not equal? As I was going through the pages in the book, I saw an interesting section with a new word that I have not ever heard about, which is the concept of purge.
Purge as an English word means remove something, as in get rid of group of people from an organization or from your life, or get rid of that feeling that you have, whether sad or happy or whatever. But in chemical engineering, it means removing the impurities, the things that make the system not reach a steady state. We need to have a steady state process, like what you see in the refinery and petrochemical industries. They always have their process steady state. Any large scale process needs to be on a steady state. And without purging the system, we will have this math error, which is if you add these together, it will not be the same as 482. If we purge the system and create something here, there will be actually mass M equals to mass out. To have the idea perfectly understood, let's solve an ammonia production plant example and prove that really we need purging when we have inerts. We have a system that is composed of a reactor, separator, and a purge stream to form ammonia. We are given the fresh feed information with each number of molar flow rate and the reactor conversion of 40%. We are given that the separator will remove all of the NH3 but will remain the 3 components that will be split by a 1% purge fraction, while the rest will be recycled back to the reactor. The big deal or the question is to find the number of moles of ammonia produced per second. But before solving, I want to show you the power of purge, 382 and 10. This will make the balance around the mixing right. And now we start with clarifying that S is for separator and R is for reactor. Things are still not balanced chemically, so we will balance them to make the material balance later on right. And then, as in every material balance problem, we start with labeling all the information and then do the degrees of freedom analysis. Specifically around the mixing point, we have 4 unknowns, nitrogen and argon from stream 1 and nitrogen and argon from stream 6. We don't count hydrogen as unknown because it is dependent on nitrogen. So we would choose nitrogen with argon or hydrogen with argon. It can't be both, hydrogen and nitrogen together. We have a split fraction of 1%. We call it purge fraction. And the other one is fascinating. It is the fact that we have sharp separation, which means all of the ammonia will be separated from the 3 components argon, nitrogen, and hydrogen. This will make the degrees of freedom analysis 4 unknowns minus 2 independent equations minus 2 pieces of information. You can go ahead and start with the balances, but you will end up having only 2 equations with 4 unknowns. This is a trouble for us because if we want to proceed, we need another method because the degrees of freedom told us that the system is solvable. Here is what I like about purging. The split fraction allows you to express a stream in terms of the other. And this is what we are going to do in this example, and this is what you are going to do in the exam when you face purging problem, especially this case. Having that established, I will show you the roadmap from N6 all the way to N1, starting by a simple mass balance around the split point. If the 1% is the purge stream, then 1 minus the 1% will be the stream that is going back to the reactor. And from the sharp separation, that the streams before the separator should be the same after the separation. And the last step here is to do balance around the reactor. I repeat, if you found nitrogen, you will find hydrogen. But let us now express the xi, it's the extent of reaction.
We have already the fractional conversion given, single pass conversion 0.4. Multiply it by the limiting reactant, the nitrogen going to the reactor, we call it feed to reactor, and then back substitute it into the nitrogen N2 equation to find the nitrogen leaving the reactor. Now go back further to N6 equation, and then you will have in the end an equation like this. And now if you do mixing point balance, you will substitute instead of N6 that is there in the mixing balance, you will replace it with the expression from N1, and the same goes with argon, but argon here is simple because it is non-reactive. Solve it now for nitrogen N1, and if you multiply this number by 3, immediately you will find the flow rate of the hydrogen going to the reactor. Do the same thing with argon, find the mole going to the reactor, which will be basically the same leaving the reactor. Doing so, we will only be remained with one step, final step, to identify the whole stream going to the reactor. Now comes the real fun. All of us later on will agree that we will be so happy if we are given a question about Purge in the exam. We already have established all the equations leading us from the reactor all the way to the split point. These will be the flow rates leaving the reactor, which will be the same as those going to the split point, remember the sharp separation, and this will be the results of the three components for the stream recycled back to the mixing point. If the recycling fraction is 0.99, then the split fraction will be 1%. Just do the exact same equation, but replace 0.99 with 0.01 to find the purging stream. For the ammonia, I will leave it as an exercise for you to figure out how to calculate it. Remember, it is produced, not consumed. You did your material balance on all the systems and you found all the flow rates. How can you know or how to tell if it is correct or not? This is the most important question, and it will help you whenever you solve a homework, an assignment, or if you just have an additional time in the exam. To answer that, we would need to come back to the first concept I introduced, which is the mass conservation. In other words, you need to do atomic balance. The moles that came in, it will be the same as the moles that will leave. Knowing that, you need to perform an overall atomic balance to find out that really the left-hand side is equal to the right-hand side for all the components.
And you heard me right when I said atomic moles are conserved, because they are in terms of atoms. No need to bother yourself to convert every mole flow rate into mass flow rate using the molecular weight. I wish I had this knowledge before when he asked us that question. But I can't go back in the past and correct everything that I have done wrong. For you, you can. And in this channel, I will make sure that every video you see, you will come out of it with a very, very powerful benefit. See you soon.